Hello, everyone. Good afternoon. My name is Moti, and I'm going to talk about how you can get security insights from your server logs. I will start by introducing the general concept of what it even means viewing your server logs for security. I will continue with a few detection rules that I run in my own environment and how you can create your own signatures for your applications. Continue with a few lessons learned at Wix regarding scale and distributed systems, and leave with some thoughts for the future. This talk is especially relevant for you if you are a security engineer or a developer that writes some kind of custom code at your company, which is probably everyone here. If you deploy any kind of application to a server, then it's relevant for you. It is also relevant for white box vulnerability researchers that try to find vulnerabilities in applications that they run locally. Let's do a quick survey. Who here collects server logs, like backend server logs? Okay, cool. And who here monitors the server logs for security issues? Great, really good numbers. As for me, I used to be a consultant for many years. I used to do a lot of penetration tests and red team activities. And in the past 2 years, I work at Wix as part of the application security groups. And in my day-to-day work, I'm kind of the blue team. I work with the developers, making the product more secure, preventing vulnerabilities from getting into the production environment. And what is Wix? Okay, we are a large website builder. We are one of the largest website hosting companies in the world. We run like 7% of the internet websites. We have millions of users, thousands of services, and tens of thousands of different APIs. Some of them are exposed to the internet, some of them are internal, and we are really outnumbered in terms of application security. We have lots of developers, but very few application security engineers. So the challenge is really great, and we need to automate everything that we can do. And the story of how we monitor application errors started about a year ago. So for several years, we thought that, let's take SQL injection, for example. We thought that it was dead. We didn't have any SQL injection vulnerabilities discovered in our applications. No one reported this to us. Not bug bounty, not internal penetration tests, not code review, not automatic tools. And the only thing we got from automatic tools was actually false positives. But we started monitoring our application errors, like the backend server errors, and only in 1 year, we discovered lots of critical vulnerabilities that we closed in production. Now, going back to my penetration testing days, whenever I saw this type of error, I was very happy because it meant for me SQL injection, right? It was so obvious. And I really like SQL injection and attacks of this sort because they don't rely on the context of what the application can do or the data that is stored inside it. You can skip into the operating system and then go into the organization deeper. And what I believed back then was that this attack is kind of stealthy. It doesn't generate a lot of noise if you do it correctly, like not in some automatic scripts. If you do a clean SQL injection attack using your custom payload, then probably no one will discover you until the point that you reach the operating system. And if you take the patterns of how attackers attack applications, you can separate it into two different buckets. So one pattern is attacks that are against the application logic, things that are mostly product related. If you do a brute force against the application, you do password spraying, authorization issues, you get to the admin pages, etc. And these are noisy attacks. And there are attacks against the runtime itself, things like SQL injection, SSTI, Log4j, things that the developer or the product, the person who developed the product in general, he didn't think about it and he doesn't really know about it. Things like Spring4Shell, deserialization, etc. And these types of attacks create different signals that we can use, signals that we can see in the logs. Now, let's take a regular flow into some application. I oversimplified it, but this is how it looks like. A user sends some kind of a request to your server, let's say through a REST API. It will first hit some HTTP server. We use Nginx, but you can use whatever HTTP server you want. This is not the application yet. This is just some kind of a middle tier between the user and the application. you can see lots of data in these logs, HTTP access logs, get, post, the size of the request, the response type, etc. And then there's interaction with the application itself. At this point, once there was some successful interaction with the application, the developer writes logs. You can separate it again into two different types of logs. There are the things that tell the story of what happened technically in the system the developer wrote, and he wants the logs should be read by the developer, by the developer's team, and not by some product or someone who understands the flow of the product. Things like sending Kafka message to some topic or some exception that an account wasn't found. Sorry, not much of a security person, huh? And there are the things that we call BI events. These are the logs that tell the story of what happened logically in the system. Like they tell the story of the product workflow. Successful login for some user, or user published some website. And we at Wix separate them into different databases. They can be also stored on the same database. They can be written to the same log, but we have like these different flows and different log pipelines. There's this great project called OWASP AppSecEU. What happened? Sorry. Okay. Raise your hand if you're familiar with OWASP AppSecEU. Okay, cool. It's a great project. It provides this both technical and more logical framework of what you need to do with your own logs. Like it shows you the steps that you need to take to understand if someone is attacking you and what you need to do in order to protect yourself from it. And it talks about all of the types of the logs, including access logs, BI, and developer logs. But I'm going to focus specifically about the developer logs and specifically inside them about the errors. This is the 1% that interests me. Now let's take an attack floor, for example. We have some attacker running some script, SQL map. Again, it will hit the Nginx server. It will write lots of logs into the access log. But does that mean that this attack was successful? Or it just means that someone is attacking me? Well, someone is attacking us, Wix, all the time. We get flooded with attacks, and it's really, really hard to separate the noise from the successful or the interesting attacks. And 99% of the data that is in the access logs is irrelevant for security insights. You just know that you're being attacked. Okay. But that 1% of the interaction with the application itself. Let's say the SQL map found an API that is sensitive to SQL injection. No one found it. It reached the production environment. Bummer. Now the application created this vulnerable query, communicated with the SQL database, and the database returned a SQL syntax error. It will be reflected in the logs. And this 1% is the percent that we're looking for, and it tells us as security engineers that there is a problem. Even if it's not an attack, there's probably a problem because it came from user input. And if you see these types of exceptions in your production environment, it's not good. Now, this is just one example, but you can also look for other signals and other signatures of these errors in your logs. Let's have a look how it looks like. So again, SQL injection, you will see, can you see this? Is it too small? You will see this in the access logs. It doesn't mean that the attack was successful. But again, if you see something in the application error log, something like this, then it's probably a vulnerability SQL injection. And once you get the alert from this suspected SQL injection, what should you do? You get like alert with a stack trace that said, you have a potential vulnerability here. How should you analyze it? So this is a stack trace. It consists of the class that generated it and a message marked in blue, and then a sequence of the classes and methods that calls this that created this exception. Now we're not really interested in the classes that are generic, the things that we don't control, the code that we did not introduce the vulnerability. So this is kind of we need to skip these classes, and then we need to analyze specifically the class that is part of the package that we wrote, the code that we have control over. And this, for example, it is calm with something. We can see the class, and in red we can also see the function that created this exception. And this function is probably susceptible to SQL injection. And the same analysis goes for every vulnerability. And this example is for JVM-based systems. We use Scala, but you can also, it also applies, for example, for Node.js, for PHP, for whatever you use. Let's take server-side template injection. So an input of an attack would look like this. If you know payload all the things, it's a great repository, a cheat sheet with lots of different attack payloads. So we all know how a payload looks like this. And SSTI, if you're not aware, it's a vulnerability that involves template engines that render stuff on the server side. And they are very, very, they have like superpowers, and they can call classes inside the runtime. Not all of them, by the way. There are some template engines on the server side that are pretty secure. But most of them have superpowers. They can call classes. They can actually call the runtime and execute commands. So in most cases, SSTI means RC. And you have all of these different syntax, different rendering engines. We specifically use a few. I will show you an example about velocity. So these are the inputs, and inputs don't really interest us. But if you see some exception regarding rendering of the vulnerability, for example, Apache parse error exception, the velocity, this is something that we use. And I found personally a few RCs in my application landscape using this specific exception. Same goes for XXC. Again, vulnerable XML parsing. If you see this input, it doesn't necessarily mean there's a vulnerability. But if you see exceptions regarding XML parsing issues that you can combine with some input, that malicious input, then it's a red flag. We don't use XML in general, and I was really surprised to see these exceptions, but there are these edge cases where you do parse XML, apparently. Now, you run your own applications, you have your own framework, and you want to create your own signatures, right? Not everyone is interested in XML because they don't parse XML. In order to create a signature for your detection, try not to think about what would the attacker insert into the system. Think about how would the application behave, or what errors you should expect to see at your logs. And let's take, for example, I created some kind of a vulnerable application. So you need to create or run some kind of a vulnerable application locally, either Juice-Shop, WebGoat. I created my own Spring framework. And if you're super lazy, like me, you can use these tools that provide you labs with vulnerabilities. I use Secure Flag, amazing. And you need to trigger the vulnerability from one side and then examine the server logs from the other side. If you see some kind of weird errors coming on the server, that means that you may have a signature to base your detection on. And let's see a demo. Can everyone see? Cool. So on the top, I have application, some API over Spring Framework that is vulnerable, that accepts an input and parses it in some rendering engine called Spring Expression Language something. And this is a fancy name for a template engine. And this vulnerability actually means RC. It's called spell injection. So I run the application, the vulnerable application locally. And now I will turn on burp. And I have this pre-ready request that sends the payload, sends some string to this API. The API should echo it back to me. Now I want to insert some RC payload. And look at the payload. I just wrote AAA because it's just testing, right? In some cases, the exploit can be super clean. I can write bin, bash, do something, reverse shell, whatnot. But in some cases, there are these just exceptions that happen. Some weird input got into the system. Someone wrote his name in some weird language that the rendering engine doesn't know how to respond to. And in some cases, the binary doesn't exist on the operating system. So this binary, AAA, doesn't exist on the operating system. Oh, sorry. And as an attacker, I got some exception, but now I can see, if you see an error over here, And I want to examine this error to understand if this is something that I can use as a signature. Now, if you see this specific exception in your own logs, it means that you probably have spell injection, right? And you can do the same process for all vulnerabilities out there. By the way, you can also see a signature for RCE in Java. If someone is trying to use process implementation and you have exceptions regarding process implementation, then again, it means RCE probably. And it won't appear in the input because the input looks differently. So the false positive rate is really low. Okay. So once you get the point of how you run signatures, create signatures, and look at these logs, there are cons for this kind of monitoring. First of all, it conflicts with the shift left approach. Everyone says, why do you monitor things in production? You should prevent things from going into production, right? You should prevent vulnerabilities. But we all know that this is not really the case. It would be naive to think that vulnerabilities don't make their way into production. We know that for fact in this case. They would also say it's too late. You don't want to detect the vulnerabilities only after the exploitation. You want to detect it before they are exploited. In addition, it's not a silver bullet. Not all vulnerabilities can have matching signatures that you can create, and not all exploits generate noise. Some exploits are really, really clean. They don't generate any exceptions, like a single request exploit that pops in reverse shell, and you wouldn't see it in some error. And one pain that we have is that developers can swallow logs. They can hide logs and not write them into the log or replace them with some other exception. So it's not a silver bullet, but it's really easy. First, you find vulnerabilities and not just exploits. We found most of the numbers that we found were vulnerabilities and not exploitation attempts. In addition, you can monitor all your running code, everything that is in the runtime, including code that you don't control. For example, SDKs, jars, some kind of external import, something that you don't have the other tools to work with, like static code analysis. You can also have visibility for entire on-premise solutions like Jira if you run it locally, or some black box that you put on a server. You can monitor its logs. It has minimal false positive rate compared to, again, to the perimeter-based analysis, and I will get to the numbers a little bit later, but it does have some false positive rate. It is continuous. You can catch things that were introduced a day ago by some developer that didn't want to tell you about some new API that he wrote. And it doesn't cost anything. You don't need to buy any product. You don't need to do anything. Everyone here collects logs. You raise your hands. You just look at the logs, query the data, and you find vulnerabilities. And it acts as kind of a safety net from the right. Everyone says shift left, but I also say protect from the right. Now, at Wix, we ran this kind of program. We understood its value. And after 1 year, we have these lessons that we want to share with you. So first of all, we started off as, why not just use some existing tool or product that does this for you? We examined a few RASP solution, and there was a great talk about RASP here yesterday. For those of you who are not aware, it's a category of products called Runtime Application Self-Protection, which is the best name ever. It is a category of solutions, security solutions that attach themselves to your application as either instrumentation or some even eBPF and some other technologies, and they protect your application from inside. The problem with that is some of them make impact on production, at least the things that we tested. Well, all of them have some impact, but maybe it's minimal. It does consume CPU, it does consume memory because it's another application that runs on top of your application. It's some other logic. In addition, we have trust issues. These tools are kind of black boxes, and we don't have a way to extend and add your own controls over them. And again, I'm talking specifically about the things that we tested. Maybe there are great tools out there. But that took the RASP out of the equation. And what about endpoint protection? For example, we spoke a lot about RCE. You can detect RCE, you can detect RCE. EDRs and things and tools that are endpoint protection tools that are aimed at the operating system. They can detect RCEs and exploitations and reverse shells, right? But they don't have the context of the application. They don't care that you have a vulnerability. They don't know about SSTI. They just understand RCE. They understand what an attacker does on the operating system level. So it's also out of the question. Now, to understand how we work, you need to understand our architecture. So we have this big production environment with the 5,000 microservices that I told you about. It runs in the main production environment. But we also have this distributed nature of architecture. And I guess in lots of big companies, you have the same pains. We have subsidiaries, companies that we bought that run their own application stack in their own environment, in their own infrastructure. You can run on AWS with EC2 servers. You can run on Lambda. You can run on GCP. You name it. Our developers and our sub companies, they have their autonomy to do whatever they want. And it is difficult for security because for this type of monitoring, we don't have any single log pipeline. We have these pools of data that exist everywhere, but we don't have a single log repository we can work with to query all the data. And just to query the production data that we have from the big cluster, it's a massive scale. We're talking about 130 terabytes of data. Querying this information is really, really, really intensive, and big systems that we have start to break once you start to query a long time ago. In addition, we run all runtimes. We use JVM, we use Node.js, Ruby, .NET, Python, you name it. So it's kind of a challenge to be able to create signatures for all of these runtimes. So in order to handle the scale and the complexity of Wix, we created an internal tool that I hope we can release as open source as soon as possible. But first we need to do some battle testing and POC internally. It enables us with easily onboarding all of these different application runtimes and log sources into one single pipeline. It also allows us to take only the relevant information that we need. Remember this 1% that we are looking for? So we are not interested in the 99%. We can send them to some bucket, some storage that doesn't cost any money. We don't need to index this information. We just need to parse it and get the specific logs that we need. It is super cheap. It only costs the CPU that it consumes, and it's super effective. So you don't need to pay for licensing, storage, and all of this. It has a modular rule engine, like all of these other tools, and it's vendor neutral. We don't need to log into a specific solution. We can use logs from this source. From this source, we can replace the solution, the SIEM solution that we use in a year, and we're not locked into something specific. Now, after 1 year of monitoring, we do have false positives. Although I said it's a minimal false positive, but we still have false positives. And if you get this type of monitoring of your application runtime, you will need to manage some kind of whitelist because you don't want to handle noise, right? In addition, analyzing these alerts is not as easy as you would think. So we have an alert. I got an alert with some stack trace. I got into the code, and one time I see this library that queries database. One time I see another library, another ORM. We have like 10 different ways to interact with databases, and all of them look vulnerable because the query looks really weird and vulnerable, but apparently the library does some protection for you. You need to understand the syntax of each, and static code analysis doesn't always know how syntax of a specific library works. So when you analyze these alerts, you need to understand the code, and it's pretty difficult, specifically for Scala, because no one understands Scala. In addition, we have these exceptions that come from perfectly safe queries. Apparently, you can have a safe query, select something from something, and have an empty in clause. This part right here, I know, can you see my screen? Okay. Sorry. So if you have an empty in clause, even for a safe query, it will generate an exception. And it's a big pain point. So we kind of try to whitelist it. Like I said, 90% of our alerts resulted in vulnerabilities that were found. They were not attacks. And I want to stress this out. This monitoring is a tool to find vulnerabilities, also to find attacks, but it's not just an incident response tool. You don't monitor your logs just for incident response. You can find vulnerabilities out of it. And the 10% were actually attacks that we caught our bug hunters trying to exploit SQL injections that they found in real time. So it was pretty cool. Like, no one really attacked us and exploited this vulnerability from malicious intent. Another really nice story is that we found vulnerabilities in third-party integrations. So we expose an API that works with some third-party integration in the architecture of SPI, it's called. So we got errors from third-party saying that there was some syntax error with database that we don't even use. And it was really nice because we reported them the vulnerability. I don't know what they did with it, but it's really nice to find vulnerabilities that you don't even own. Accuracy. So it really depends on the vulnerability type. There are these rules that generate a lot of false positives. For example, SQL injection, 76% were actually false positives. So from all the alerts that we got, only 24% resulted in real vulnerabilities. That is because of the empty in clause, which annoys me until today. SSTIs, we got 100% false, true positive rate. That means, like, for every alert that we got for SSTI, it was a vulnerability. We opened a critical bug and it was fixed immediately. And for XXE, we got 50% of false positives, but it really depends on your application landscape. If you work a lot with XML, then you need to fine tune the rule, because this is just a parsing exception and not necessarily vulnerability, like a vulnerable parser. And by saying alert, I mean like a specific combination of a service, like a server that we have, for example, invoices, and some API method, because a service can expose 100 API methods, and one of them will be vulnerable, 99 won't be, but I can't whitelist the entire service, right? Okay, we did it pretty fast, I think. I have some thoughts for the future about how we can continue with this type of monitoring. So first of all, we are exploring right now data science, and I promised I would say AI only once. We talked until now about signatures. They're nice. They help us with the known knowns, but there are these unknown unknowns, these attacks that no one really knows how to generate signature to. And machine learning algorithms can help us with finding them. We are looking at the direction of taking, for example, a service, and again, we have 5,000 services, and over time understand how it behaves, it behaves in terms of errors. So how the errors look like and how the stack traces look like. And if they all look like the same, it's probably not something interesting unless everyone is attacking me all the time, which is really bad. But this 1% of the exceptions that we have can be really interesting in terms of security. It can also tell the story of really weird bugs that will help developers. But as a security person, I'm interested in security. So this 1%, I can analyze and see if I can get like a new security insight out of it and generate a new signature. And I actually asked OpenAI, what does this stack trace mean? I threw a stack trace containing something that looks like SQL injection, and he immediately understood it. So it's pretty cool. You can fully automate the process, like get anomaly detection and then ask OpenAI with the API, what does this stack trace mean? If it says it's a vulnerability, then good, I'm covered. I didn't even work. I opened a bug to the developer. Thank you. Collaboration. So like you see, there's a lot of common ground between all developers. It doesn't matter if you work at Wix, at Google, at Uber, Facebook, whatnot. We're talking about the things that consist the runtime of the application, the frameworks that we all use. And I'm not talking about specific products. There's a great project, again, OWASP AppSecEU. Check it out. It provides a really great framework of what you need to do when things happen. It opens up your mind. I created an open source Sigma rules. And for those of you who don't know, Sigma is kind of a standard. It's a great open source tool. It's kind of a standard that says how you create rules to find security issues at logs. it has I think it doesn't have enough buzz, but you can have like a Sigma rule and then convert it to Elasticsearch, to Splunk, to whatever SIEM that you use. So this is the place to contribute to. So check this link after the slides are released. I can also share the slides with you if they're released in a lot of time. And I also created an open channel for discussions. If you have some insights that you want to share, if you have questions, I want it really to be alive and interactive, and I want it to be transparent and have everyone on board with this. I guess that like you will have your own insights and everyone will get benefit out of it, the rules that you create. So to summarize, if you're not doing it today, add it to your to-do list, drop everything, start looking at your logs. You will get really surprised from what you see. Application logs, they're far better than HTTP access logs because they tell us the story of what happened inside the application and how it behaved, and not just who attacked me and what the attacker did. And again, it's not a silver bullet. It's a great technique. It's not the only technique out there. You can also add your own tools on top of it, but it is so simple and so stupid that everyone needs to do it because it's zero effort, right? And with that, I'm done. Thank you. Questions? Anyone? Yeah. Yes. I have a personal experience. We work with Splunk, and again, I could create rules for Splunk, but half of this room probably don't use Splunk. They use Elastic or some other tool. So I really want it to be as open source as possible, and I want everyone to be able to collaborate. And if you use Splunk and you use Elastic, then we can all share the same rules. Is there?
Pretty much you define the same rules using for Splunk.
Yeah, the Sigma, I check it out. It's a great project, really. Sigma is this tool that runs YAML files. You can convert it from one language to another, like from Sigma rule to Splunk alert or to Elastic or to whatever technology you use. It's a great project. You have to check it out. Yep. Like I shown you, we have like a centralized production system where we have most of the logs, 100 something terabytes. But again, we have these islands of different products and different sub companies that we have that they use their own infrastructure. So it's kind of, we don't have access to these logs, and it's really hard to onboard them back into our central place. This is why we created the tool. It's really hard. I'm not telling them to use the tool. I'm telling them just give me the logs. Send your logs to some HTTP endpoint, or send the logs to some S3 bucket, and I will take them. That is it. And I will all parse them. Yes.
I'm not sure if I understood it correctly. You mentioned that you have to try to learn from the errors, like the causes of errors, and use machine learning for that.
We are testing it. Most of the slides did not mention machine learning. This is just regular signature-based detection. But we are exploring the machine learning part to learn how an application behaves over time. Yes.
Okay. Related to that, your opinion, what seems to be the best candidate for algorithm for learning behavior?
I honestly can't say. We have data scientists. Which is not me. I'm not a smart person. We have data scientists in the security group that handles this, but he uses it's not really machine learning. You just, honestly, you take the stack trace, you break it down into different nodes, and then you collect the anomaly rate, and then you convert it back again to the stack trace to understand what appears a lot and what doesn't appear a lot. It's not like super scientific machine learning algorithm, like shiny thing. Once we have maybe a model that we can release, I hope we can share it with the world. Yeah, but we are just testing it right now. It's just a POC phase. Yes.
Can I ask
here's the exception. Isn't that an exploitation payload of the time? And what are the other conditions?
Definitely not. It's not in, like, we have tons of traffic coming into the application. And again, if you have some comma in your name and it means something in the syntax of this engine, you're not an attacker. It's not an exploit, but it did generate an exception, and it does tell me that there's a vulnerability. So like I said, 90% of the alerts that we got, they're not exploits. They're just weird payloads that come into the application.
So I think these actually exercising each that point of payloads, like exploitation payloads for each class. Then you can enumerate additional can find vulnerabilities instead of just these deeper traffic, like regular traffic that you get from the users.
Exactly. We connected this type of monitoring with from the other side with fuzzers. So we have this dynamic analysis tool, Dust, that attacks our application from one side, and then we look how it behaves from the other side. If we see like high error rate and the specific errors that interest us, then this means that there's a vulnerability. We still haven't connected the dots to have like a full cycle back to the Dast to understand that the vulnerability occurred, but we have the human connection. We know that there's Dast scanning on one side, and then we monitor with our eyes on the other side. Okay. Yeah, sure. So Visla, again, we have this problem of the distributed environment. We have lots of different applications and islands of runtimes that we don't control. And we found out that it's really hard to collect all the logs from all of these sources because, again, we use a specific commercial tool, and to connect all of these sources, we need to provide them keys, and we need, if it's cross-region, then it costs a lot of money. So we need this tool in all of the regions, for example, in West United States and in Central Europe and all of this. So the tool is actually a pre-processing layer before our SIEM, and it only needs to be able to get more log sources into the system, to onboard them, I mean. And it is really, this is the main part, to onboard different log sources and to sift only the relevant data that we need. We don't need to index all of this data. I just need to find the specific strings or the matching of the logs that I need. And I don't need the 99%. They are already logged somewhere. The developer logged them. I don't care about them. This is the developer's job. And I really hope we can release it as open source. We have like lots of different things going on. We will first test it locally, see if it works, and I really, really hope we can release it as open source as soon as possible. And you can also contribute. Feel free to test it out in your own environment. Yes.
Questions asked one was already mentioned, and yeah, that is a proprietary commercial product, but the detections are actually open source under a Apache 2 license. So I was wondering if you imported any type of detections that Splunk has already developed. I was also wondering about scale. You mentioned you have it about 100 some terabytes.
Yeah.
How much data are you bringing in every day for analysis?
So every day I bring, I think, around 20 terabytes, and it's like a rolling process where we delete all the logs from the past. Regarding, again, specific commercial tools, I did test out their rules. I did look at Elastic rules and all of these other tools. They are not focused on application security for some reason. Only the only rules that mentioned some kind of AppSec related stuff was Datadog. They created these rules from a company they bought years ago called Screen. But it's not, at least from the things I saw and the research I done, it's not mature enough. You don't have enough rules. And again, I don't want to disrespect any commercial product. I just want to have it like as open source as possible, to have it not in a single product, but to like as intentionally I contributed to the Sigma project because it converts these rules to all of the different commercial products. Cool. If you have any more questions, feel free to reach out to me directly and join the Discord channel. You have more questions? Okay.